All right, so your last few videos finally showed you what the fundamental theorem of calculus is, parts 1 and 2. We finally have this connection between derivatives and antiderivatives, and we see a little bit of how that all relates to the exact area under some graph of a function. What I want to do here is just show you a few specific examples of using the fundamental theorem of calculus part 2. And let me start by just kind of restating that theorem. Suppose we have a function that's continuous from a to b, and capital F, be careful with the notation here, I have a lowercase f and a capital F. Capital F is some antiderivative of this lowercase f. And I want to do the definite integral of lowercase f from a to b. All right, so in other words, remember that if we're thinking of this as an area application, then I've got some function, f of x, that's continuous between a and b. And if I can find out what number this definite integral gives me, then I'm finding the exact area under this function between a and b. What the fundamental theorem of calculus tells us is that to find that exact area underneath this graph, you take your antiderivative, capital F, and evaluate it at a and b and subtract. One little piece of notation that I'll show you that I don't think you saw in the last video. Sometimes we write this this way, capital F of x, and then we have like a vertical bar. When you see this vertical bar in math, it means you're evaluating it at some number, and then you'll write a and b, meaning we're going to evaluate this antiderivative at a and b, and we're going to subtract those values. So when you see this vertical bar with these numbers attached to the top and bottom, that means to plug in b, plug in a, and subtract. So you've got f of b minus capital F of a. All right, so let me show you a few examples. Let me start with some simple functions, and these are ones like this very first one. You could do this without the fundamental theorem of calculus. This is just a straight line, and in the last section we used geometry to find these integrals. So if you like, go ahead and pause the video and find this area using basic geometry. And then let's see if your answer matches what we get here using the fundamental theorem of calculus. So according to the fundamental theorem of calculus, I need to know the antiderivative of x. X to the first power, so I'm basically doing this power rule backwards. I've got x to the first power. I need to add 1 to the exponent and then divide by that number. So 1 divided by 1 plus 1, I would have 1/2 x squared. Now, when we do our indefinite integrals, usually we write a plus c here. When we do these definite integrals, we can basically, in this case, I guess you could almost say we're ignoring the plus c. Really what we're saying is we're just assuming that c is 0, because let me go back to this theorem. We're saying that capital F is an antiderivative. There's infinitely many antiderivatives of f. This theorem works for any one of those antiderivatives. So when you see this, then the easiest antiderivative to pick would be the one where c equals 0. All right, so when we see this, let's pick the antiderivative where that integration constant was 0, just to make our calculation a little bit easier. All right, so it's not that we're completely forgetting about this integration constant. The truth is that this will work no matter what constant we add here. So let's just simplify things and assume that that constant is 0. All right, so we got our antiderivative. You can double check this. Take the derivative of that and you get back the function that we had inside the integral, right? The derivative of 1/2 x squared is x. But we're not done yet. To finish this definite integral, I have to evaluate it at 2 and 0 and subtract. So I'm going to 1/2 x squared evaluated from 0 to 2. So that means I need to do 1/2 times 2 squared minus 1/2 times 0 squared. All right, so that's 4 times 1/2 is 2 minus 0, 2. All right, so if you did this integral using basic geometry, you should have gotten the same answer. All right, let's go ahead and go, let's go down to this sine function next. The integral from 0 to 2 pi of sine of x dx. If I'm going to use the fundamental theorem of calculus, what's the antiderivative of sine? Well, let's see. It's probably something related to cosine, right? Is it just plain cosine? If I check this, the derivative of cosine is negative sine. I don't have a negative here. I need to compensate for that. So I think negative cosine should work, right? If I do negative cosine x is my antiderivative, again, double check that. What's the derivative of negative cosine? The derivative of negative cosine is negative sine, which is a positive sign. All right, so I've got negative cosine x, and I'm going to evaluate it from 0 to 2 pi. All right, so now plug in 2 pi, plug in 0, and subtract. So I've got negative cosine of 2 pi minus a negative cosine of 0. Now, if you think about your unit circle, cosine of 2 pi and cosine of 0 are the same thing. They're both 1. So I have -1 plus 1, which is 0. Now, let's stop and think about this for a second. Why did we get 0 for our answer? We actually talked about this in a previous video. Think about the graph of sine of x from 0 to 2 pi. This function that we're integrating from 0 to 2 pi is this. That's one full period of the sine function. So what did my answer come out to be? 0. Well, it came out to be 0 because I have just as much positive area as I do have down below the x-axis and negative. If you have just as much positive area as negative area, then they'll cancel each other out, and your answer will be 0. All right, so if we had thought about this for a second geometrically and knowing what the sine function looks like, maybe we could have known what the answer would have been without even using the fundamental theorem of calculus. But it's nice to see that the fundamental theorem of calculus works out to give us the answer that we would expect geometrically. All right, coming over here, the integral from 1 to 2 of 5x squared, and then the integral from -1 to 1 of x cubed. This would be a good place to go ahead and pause the video and try these on your own. One thing I would suggest is, remember we have these properties of integrals. One of them is that the 5 can be pulled outside. So just to simplify your work a little bit, focus on doing the antiderivative of x squared instead of the antiderivative of 5x squared, and then just multiply your answer by 5. All right, so 5 times the integral from 1 to 2 of x squared, and do the integral from -1 to 1 of x cubed. Both of these are just basic power rules again, the antiderivative version of power rules, right, where you're adding 1 to the power and then dividing by that number. So it'll be one thing that I suggest that you do. A lot of people get mixed up. They've been doing the derivative version of power rules all semester long, and now all of a sudden for antiderivatives, you're doing the opposite of it. So something you should sit down and do is just practice switching back and forth between power rule for derivatives, power rule for integrals. Switch back and forth so you can get used to using the right rule at the right time. Okay, that's just one of those things that comes with experience, and the only way to get efficient at it and cut down on your mistakes is to do it lots of times. Okay, all right, so go ahead and pause the video if you haven't already and try this out, and then press play and see how you did. All right, so this first one, The antiderivative of x squared is 1/3 x cubed. So I have 5 times 1/3 x cubed. And again, normally with an indefinite integral, we would write a plus c here. But with a definite integral, we can assume c is 0 and it'll work out fine. All right, and we are going to evaluate this from 1 to 2. So I've got 5 times 1/3 times 2 cubed minus 1/3 times 1 cubed. All right, and here I left the 5 outside of the parentheses. I'm just focusing on this integral without the 5 first, and then I'll just multiply everything by 5 at the end. All right, so we did our antiderivative, we plugged in the 2, we plugged in the 1, we subtracted, and now it's just some basic simplifying or calculator work or however you want to approach this. Let's see, let's just clean this up a little bit. That would be 8/3, 8/3 minus 1/3. So that's 5 times 7/3. So we have 35/3 as our final answer. All right. How about this last one on this page? The antiderivative of x cubed is again just your backwards power rule. You add 1 to your exponent, so you'd have x to the 4th. And then you have to divide by that number, so 1/4 x to the 4th. And we want to evaluate this from -1 to 1. So I need to do 1/4 times 1 to the 4th power minus 1/4 times -1 to the 4th power. And what does this give us? That's 1/4 times 1 minus 1/4 times 1. So that would be 0. And again, this is actually kind of the same idea as what we saw with this sine function a second ago. This x cubed function, if you look at this function over this interval from -1 to 1, we know what this function looks like, our basic x cubed function. If we're going from -1 to 1, since it's symmetric across the origin, you have just as much positive area as negative area again, so everything's going to cancel out and give you an answer of 0. So again, this is one of those cases where geometrically, maybe we could have guessed what the answer was without doing the fundamental theorem of calculus. But again, it's nice that we do the fundamental theorem of calculus and get the kind of answer that we'd expect based on our understanding of positive and negative areas under graphs. All right, one more page where I'll show you maybe some slightly uglier examples, but really, if you're comfortable with your antiderivatives that we practiced back in section 4.8, then they shouldn't be too bad. All right, so let's look at these, and again, go ahead and pause the video here, see if you can figure these out. And again, I'll mention that we have these properties of integrals that we can take advantage of. So for example, in this first one, I can break things apart. I have a sum of 2 functions. I can break this into 2 separate pieces. The integral from 0 to 1 of 4e to the 3x. Notice here, this isn't just e to the x, it's e to the 3x, so you'll have to be careful with that 3. We talked about back in section 4.8 how to compensate for that 3. So keep that in mind when you do this yourself. Plus the integral from 0 to 1 of the square root of x. Now, anytime we're doing square roots involving derivatives or antiderivatives, we want to rewrite that as an exponent. That's x to the 1/2, so that we can easily do our integral version of the power rule. Also, this 4, if you like, you can bring that outside of this integral. And I'll mention here in this very first step, it wouldn't have been correct for me to factor the 4 out right here because the 4 was only attached to e to the 3x. It wasn't attached to the whole thing. But here, 4 is only attached to this e to the 3x, and so I've got 4 times this function. I can pull the 4 out of this first integral. So I've got 4 times the integral from 0 to 1 of e to the 3x plus the integral from 0 to 1 of x to the 1/2. All right, so just do these antiderivatives and evaluate at 0 and 1 and subtract. You might get some ugly looking answers, and that's fine. Instead of giving me a decimal answer here, just leave the answer in exact form. On your homework, if they want you to round, they'll tell you how many decimal places to round to. But here, don't worry about any decimal places. Don't even punch this into a calculator. Just write down what you get whenever you, once you plug in the 0 and 1 and subtract. All right. This second integral here is similar. You can split this up into 2 separate integrals. You can bring the 5 out of the first integral, bring the 9 out of the second integral. And again, you have a 3x inside this cosine function. Be careful and make sure you compensate for that correctly, like we discussed back in section 4.8. All right, so again, here, pause the video, try these on your own, and then we'll see how you did. All right, so real quick on this first one, if you remember, the antiderivative of e to the 3x would be 1/3. That's how we compensate for that 3. We multiply by 1/3, so 4 times 1/3 e to the 3x, evaluated from 0 to 1. The antiderivative of x to the 1/2. You do your power rule again, 1/2 plus 1, not minus 1, plus 1 would be 3/2. So I have x to the 3/2. But then you divide by 3/2, which is the same thing as multiplying by 2/3. And again, you can easily double check this. Take the derivative of 2/3 x to the 3/2 using your power rule for derivatives, and you'll see you get back x to the 1/2. And we're evaluating this from 0 to 1. So we basically have our answer. We just have to plug in 1 and 0 and subtract. If you like, you can just keep this 4 over 3, this 4 times 1/3, this 4/3. Let's just keep it outside of all this and focus on plugging the 1 and the 0 into e to the 3x. I've got e to the 3 times 1, that's e cubed, minus e to the 3 times 0, that's e to the 0 power. And here, the same thing, this 2/3, I'm just going to leave it outside for now just to keep things a little bit simpler. I've got 1 to the 3/2 minus 0 to the 3/2. I'm plugging in 1 and plugging in 0 for x and subtracting those values. E to the 0 equals 1. So this is 4/3 times e cubed. Now again, e cubed, that's some ugly decimal number. Don't bother writing the decimal, just leave it as e cubed. But e to the 0, I can go ahead and write that as 1 to clean it up a little bit. 2/3 times 1 to the 3/2. 1 to the 3/2 is just 1. That's 0, so I've got 1 minus 0, so that's just 2/3. 2/3 times 1 is 2/3. I guess I could even clean this up a little bit more if I distribute the 4/3 into the parentheses here. That would be 4/3 e to the 3rd power minus 4/3. And then I still have this plus 2/3. And let me just borrow a little bit of space from this next example. Negative 4/3 plus 2/3 is negative 2/3. So I've got 4/3 e to the 3rd power minus 2/3 would be kind of the cleanest version of my answer I could give. All right, so again, that would be what I consider to be an exact answer. All right, I'm perfectly happy with this answer right here. There's no ugly decimals that I have to worry about rounding. This is an exact representation of my answer, and this is whatever ugly number this is. Again, you can punch this into a calculator. If your homework asks you to round to a certain number of decimal places, you'll get some number. Whatever that number is, That is the exact area under the graph of this function between 0 and 1. Okay, whatever that function looks like, we know what the area of it, underneath that function is. All right, this last example, this integral from 1 to 2 of 5x to the negative 1 minus 9 cosine of 3x. I threw this in here because, for one thing, I want you to be really careful about this x to the negative 1. It looks like you should be doing the power rule, right? We've seen so many x raised to the power, and we've done the power rules. Here, x to the 1/2, we did the power rule. Back over here, we had x raised to the first power, we did that backwards power rule. X to the second power, we did the power rule. X to the third power, we did the power rule. The only time that the power rule doesn't apply for antiderivatives is when your power is negative 1. That's one of those things that's always trips people up when they're first learning this. But think about this. Remember, x to the negative 1 is the same thing as 1 over x. So let's go back to section 4.8. If I asked you the antiderivative of 1 over x, remember that was a special case. The answer was not just natural log of x, but natural log of absolute value of x. Okay? So when I do the antiderivative of x to the negative 1, this is what I'm doing here. X to the negative 1 is the same thing as 1 over x. All right, so this is the only case where you have x raised to the power where you don't use the power rule. You have to use this natural log of absolute value of x. All right, so again, if you like, you can split this up into separate pieces. I can say that this is 5 times the integral from 1 to 2 of x to the negative 1 minus 9 times the integral from 1 to 2. So I'm breaking this up into 2 separate integrals and bringing the constants out front. Cosine of 3x. I will say that after you get a little bit of practice with these, a lot of people kind of skip writing this in between step and they just go straight to writing the antiderivative. Okay, and that's perfectly fine, but when you're first learning this, it's nice to kind of break it down in smaller chunks at first. All right, so now I've got 5 times the antiderivative of x to the negative 1. We just talked about that, right? Don't do the power rule. It's natural log, absolute value of x, and we're evaluating this from 1 to 2. Antiderivative of cosine of x. The antiderivative of cosine is sine, right? Because the derivative of sine is cosine. But this is cosine of 3x, and again, just like we had to compensate for the 3 over here and e to the 3x, we have to compensate for it the same way. It's 1/3 sine of 3x. Okay, and again, you can double check that easily. Take the derivative of 1/3 sine of 3x. With the chain rule, you'd get cosine of 3x, 1/3 cosine of 3x times 3, and then the 1/3 and 3 would cancel and give you this. All right, and we're evaluating this from 1 to 2. And then finally to finish, we just plug in our x values and subtract. So I've got 5 times the natural log of absolute value 2. Notice here 2 is a positive number, so we don't even actually need those absolute values in this case. Minus natural log absolute value 1. I'm going to go ahead and simplify this 9 times 1/3. That's 3. So I've got 3, and then I'm going to do sine of 3 times 2, so it's sine of 6. Minus sine of 3 times 1, I'm plugging 1 in, so that'd be sine of 3. And again, sine of 6 is going to be some ugly decimal number. Sine of 3 is some ugly decimal number. Those aren't angles that we're familiar with on our unit circle. Don't bother with trying to write down the decimal number. Just leave it like this, unless, again, the homework asks you to round to a certain number of decimal places. One thing I can do to clean this up, natural log of 1, we should know this. Natural log of 1 is 0 because e to the 0 power equals 1. All right, so this is 0. So really the only way I can clean this up, and also I don't have to write the absolute value here because the absolute value of 2 is 2. So I have 5 times the natural log of 2. And If I like, I could go ahead and distribute the minus 3 into the parentheses, so I'd have minus 3 sine of 6 plus 3, I'm distributing a minus 3 to a minus, so that becomes plus 3 sine of 3. And really, that's as good as we can get. Every single one of these would give you some ugly decimal number. So as far as I'm concerned, I'm happy with this. If the homework asks you to round, then round to however many decimal places, just punch it into a calculator and round to however many decimal places they ask for. All right, so those are just some examples of using the fundamental theorem of calculus part 2. If you were comfortable with the antiderivatives back in section 4.8, then really these should be fairly straightforward. You do your antiderivatives and then just plug in the numbers that you have for your x values and subtract. Plug in this top number, plug in the bottom number, and subtract those values, and you get your answer. All right, so that's it. That's the end of our lesson for the fundamental theorem of calculus. After your third test next week, we're going to see some different ways of evaluating integrals. We'll learn how to evaluate some integrals where we don't just automatically know the antiderivative just by looking at it. All of these that we've done, we can just look at it and know how to do the antiderivative because we know our derivative rules. Next week we'll learn a technique for figuring out some of these derivatives where it's not quite as clear what the antiderivative should be. All right, but that's it for today.